Okay, so I'm going to be talking about supersymmetric quantum field theories. And since this is a very broad topic, the discussion is going to be somewhat broad. So I'm going to call this supersymmetric quantum field theories with a broad brush. And the way I interpreted my assignment from the organizers, hopefully correctly, is that I'll talk a little bit about elementary things and a little bit about classic results, basic results in the subject, and then I'll try to give you a little bit of perspective about what's been going on recently and sort of where the forefront of the field is as well. So there are lots and lots of places to learn about supersymmetry, and let me just list a few excellent references that I'm sure many of you have looked at before, but that are really essential in order to master the subject. And these are general references that are sort of basic for all the lectures that I'm going to give. So one is the classic work by Wess and Bagger on supersymmetry and supergravity. Another book with much more physics applications rather than just formalism is the third volume of Weinberg's QFT book. And finally, there's a very nice set of lecture notes compiled over several decades by Philip Argyris. So I think these are called just lectures on supersymmetry. And if you Google Philip Argyris' name, then you'll find his website and his notes are on there. All right, so this is going to be some exercise in holding the mic and holding the notes at the same time. So I'll try to give a few more topical references as we go along. I won't be super detailed and super exhaustive with references. Instead, I'll try to give some references that are useful, hopefully, for you to look at, and especially places to find even more references, if you're interested. Okay. So in the spirit of this broad overview that I want to give you, I've loosely decided to cover the following topic. The first lecture today will be almost exclusively about supersymmetry algebras and some of their consequences. The second lecture will be some basic overview of 4D Susy gauge theories. In the third lecture, I want to talk a little bit about supersymmetric quantum field theories on curved manifolds, on non-trivial space-time manifolds, which has been a very active and fruitful topic for the last, at least, well, going back to the late 80s, but been very active in the last 10 years or so. And then if there's time, in the fourth lecture, I want to discuss some aspects of Seiberg-Witten theory. Perhaps also with an eye towards making a connection between supersymmetric and non-supersymmetric dynamics. So we'll have a Q&A session after the lecture, but if you have questions, you should please interrupt me, raise your hand anytime. And I was also encouraged to sprinkle a few exercises throughout the lecture, so if I write an exercise somewhere, then it's something you can think about. Yes, please. Pardon me?
What is the code?
Oh, Seiberg-Witten. Excuse me?
You primarily focus on n equal to 1 supersymmetry or?
Well, tomorrow I think I'll discuss mostly n equals to 1, but on Friday hopefully I'll discuss some n equals to 2 theories as well. Today I'll try to give a sort of general overview of different theories with different amounts of supersymmetry in various dimensions. So today will be kind of all over the place. Okay. So before we get started for real, let me make a few comments. First of all, due to the nature of the subject, there will probably be some overlap between what I'm talking about and what other lecturers are talking about. For example, there will be some overlap with Paul's lectures, and you'll see some of that actually later today. There might be some overlap with the lectures from So Kim, and so forth. So if you hear something twice, that's good news, because that means that it's important and you should pay attention. And so in fact, I think that'll actually be very positive. And the other sort of general philosophical comment I want to make before we launch into the subject is just some sort of general reminder for those of you to whom it might not be completely obvious why it is that we study supersymmetric field theories. Why is this an activity that has excited us for at least 40 years and is likely to continue doing so? And loosely speaking, I see sort of 4 very broad reasons to study Susy field theories. Perhaps the most obvious one for a long time was possible applications to particle physics beyond the standard model. This has certainly been a driving force in the subject, but as of now there's no evidence for supersymmetry in particle physics, and so in some sense this body of work has to be treated as speculative, although it's extremely well motivated in some sense. Another completely orthogonal reason to study supersymmetric quantum field theories is that supersymmetry, as hopefully you'll get a little bit of a flavor in these lectures, allows you to extract exact results about strongly coupled quantum field theories. So these are results that would not be obtainable using other techniques in the absence of supersymmetry. And because of this, supersymmetric quantum field theories have sort of turned into this theoretical playground or theoretical laboratory where we can explore general ideas about quantum field theory and extract general lessons about quantum field theory. And this has been extremely valuable. And so this is more of the spirit, I think, in which these lectures will be. The third point, also very important, is that supersymmetric theories arise in and have a close relationship with string theory. We'll also see a little bit of that, and its various non-perturbative versions. So that in and of itself is a good reason to study supersymmetric quantum field theory as well. Conversely, learning more about supersymmetric field theory also tells you something about string theory. And finally, although I really won't get much of a chance to mention this at all, except maybe in the 4th lecture, they happen to be related through some miraculous connection to problems that are of interest to pure mathematicians. So it turns out that there are interesting pure mathematical problems that can be reformulated or have close connections to physical problems in supersymmetric quantum field theories. So these are certainly not the only reasons. Everybody can have their own reasons, but I think these are important ones, and they've certainly been driving factors. And as I said, I think the spirit of these lectures will orbit more around 2 and 3 than the other 2. Okay, so with this sort of general discussion out of the way, I would like to discuss in this lecture supersymmetry algebras and some of their consequences. So let me see, how far to the right can I go? Can everybody see this? Yeah, okay, and I'll keep writing here. Okay, so today we're doing Susy algebras and two additional references that will sort of guide you to the literature and give you many, many more references to look at there's a very nice paper by Chiral Symmetry, whose title I think is something like Restrictions Imposed by Superconformal Invariance. Yeah, that's what I was asking, if I should even continue writing over here. I'll give it a go. So this is a paper from '96, I think. And then there's a paper by Cordova, myself, and an Intriligator called Multiplets of Superconformal Symmetry. From a couple years ago. So the primary reason I list these two papers is because they contain a lot of references to the literature and to other foundational work. And so, basically what I'm going to do now is elaborate more on what supersymmetry is. And of course, what is already evident from the name is that it's first and foremost a symmetry. So we should discuss the symmetry algebra. That's most of what we're going to do today. And just like in any other situation where we encounter symmetry in quantum field theory, we should then study the representation theory of that algebra. And finally, the most sophisticated thing that we can do in quantum field theory beyond this is to study the sort of local consequences of the symmetry at the level of correlation functions, very similar to what Balt did in his lectures. And so that means actually looking not only at the algebra of symmetries, but also at the properties of the conserved currents. And with each layer of complexity, you'll learn a few general things and you can derive stronger results. So we'll see how far we actually get today. Now, all the theories I'll be discussing will be relativistic quantum field theories. So there'll be Lorentz invariant, in fact, Poincare invariant, so for a little while we're going to be discussing Poincare symmetry. And we're going to be in d space-time dimensions. Okay, very good. So as usual, it's good to focus on the Lorentz and translation subgroups separately. The Lorentz group in d space-time dimensions is SO d minus 1, 1. And I'll denote the generators by J mu nu. These are antisymmetric in mu and nu. And the translations are the p mu's. Okay. So supersymmetry is an extension of the Poincare algebra, where you supplement these bosonic Poincare generators by some additional charges, which in particular are fermionic. Is there a question? No. So supersymmetry, or Susy for short, is a symmetry generated by a fermionic spinor supercharge, which I'll schematically denote by Q alpha, and we'll get much more precise about the various indices in a second. And the first thing to emphasize about the supercharge is that it is in fact a fermion. So if you take the commutator of Q alpha with minus 1 to the f, which is the fermion parity operator, then you get minus Q alpha back. And remember that fermion parity is an operator that is equal to 1 on bosons and equal to minus 1 on fermions. And you can think of it as the Z2 element that extends the Lorentz group SOD minus 1, 1 to the spin group, which is its double cover. So every Lorentz invariant theory with fermions has this operator that allows you to distinguish bosons and fermions. And because this is an element of the connected Lorentz group, you can think of it, if you wish, as a 2-pi rotation. It's always unbroken as well. So that fact will be important for us in the future when we discuss supersymmetric gauge dynamics. Okay. So here I've schematically denoted the supercharge Q alpha, and I intended alpha to be a spinor index. As I said, I'll be more explicit about that. There could also be multiple Qs, and then there'll be some extra label I that labels the different Qs. So we'll get to that as well. Now, it turns out that supersymmetry algebras exist in every space-time dimension D. And what they look like schematically is as follows. The first thing is that because the Q's are fermions and are naturally anti-commuting, the symmetry algebra naturally involves anti-commutators instead of commutators. So we should try to figure out the anti-commutation relations for the Q's. And schematically, in every dimension, roughly speaking, the anti-commutator of two Q's gives you something proportional to the momentum operator P. And this gamma matrix here, which is the d-dimensional gamma matrix, translates these bispinor indices into a vector index. The reason I'm saying this is schematic is because the exact details of how this works depends a little bit on dimension. And so we'll have to discuss different cases in turn. But the basic structure is the same in every dimension. And basically what this says is that, roughly speaking, the supercharge Q is kind of like a square root of the momentum operator. Sorry, other way around. Q is kind of like a square root of the momentum operator, much in the same way, for example, that the Dirac operator is a square root of the wave operator. Okay? So this is the basic structure in every dimension. So as I said, the detailed properties of spinors depend on the dimension. In fact, they depend on the dimension mod 8. So spinors have all sorts of properties: reality properties, complex conjugation properties, chirality properties. They all depend on the space-time dimension, and they repeat periodically with periodicity 8. And if we were being very general and had a lot of time, we could do this all, for arbitrary D and use sort of the general gamma matrix formalism to do this. But that's very tedious. So instead, I'm going to just discuss those dimensions D that will actually be kind of important, that actually show up in interesting supersymmetric field theories. And that's a much smaller number. And in that number of dimensions, turns out that there are nice shortcuts for how to present the various spinors and the various symmetry algebras. So, so that's just a word of advertising. And you may ask, well, why are we only going to discuss a few different dimensions? We're going to discuss 3, 4, 5, and 6 dimensions. Why are we going to stop there? Well, at the lower end, I could keep going. I could keep going to 2 dimensions or 1 dimensions, which would be supersymmetric quantum mechanics. Those are very interesting. I'm not omitting them for any deep reason other than that I don't have time to discuss their peculiarities. But why do I stop at 6 dimensions instead of going further up? That's actually a deeper question, and that will become hopefully obvious by the end of today's lecture, maybe early tomorrow. As I said, the algebras themselves exist for any dimension, so there's some non-trivial reason why I'm only going to go up to 6. Very good. So are there any questions at this stage? All right. So we are going to start with the vanilla case, which I'm sure many of you are familiar with. This is also the case that's going to carry us through our discussion of Susy dynamics tomorrow and in later lectures. And that's the 4-dimensional case. Excuse me while I erase here. All right, so let's start with 4D. And in 4D, the Lorentz group SO3, 1, or more precisely, the spin covering group, spin 3, 1, is just SL2C. And SL2C can be thought of or can be written as a product of 2 SU2s. Let's call them SU2 left and SU2 right. But these are not standard SU2s with standard reality properties. Instead, these two are exchanged by Hermitian conjugation. So how does this manifest? Well, let me write down for you some representations of this group that you're doubtlessly familiar with. For example, we can have a left-handed 2-component Weil spinner, psi alpha. Alpha here is a 2-component index. And this you should think of as a 1/2 0 representation under these 2 SU2s. So it's a spin 1/2 under the SU2 left, and it's a singlet under the SU2 right. So I'll refer to this as a left-handed Weil spinner. And as I said, these 2 SU2s are exchanged by complex conjugation, and what that means is that the Hermitian conjugate of psi, which I will denote psi bar of alpha dot. This is sort of standard Wesson-Bagger notation to use bars instead of daggers for conjugation in Lorentzian signature. That thing transforms as a 0 1/2 representation, and that we refer to as a, if you want, right-handed Weil spinner. So these are the 2 component spinners in 4 dimensions. And the other fact we will need is that a vector in 4 dimensions v mu is in the 1/2 representation of these 2 SU2s. So it's a doublet under the SU2 left and it's a doublet under the SU2 right, which means that there's a total of 4 components. That's good. And the way to convert from the vector index notation to a notation that makes manifest the transformation properties under these 2 SU2s, you have to use some 2-component analog of the gamma matrices, which I'll call sigma mu. So there's some set of numbers or some set of Clebsch-Gordon coefficients, sigma mu, with 1 dotted and 1 undotted index, which when you contract it with v mu, give you a bispinner with 1 dotted and 1 undotted index, which is the way to transform from the vector to the bispinor representation for V. And if you want, you can easily invert this, this equation. Okay? So we have left and right-handed bispinors, and we have vectors which are also the same as bispinors. Very good. So now we have all the notation in place to write down the supersymmetry algebras in 4 dimensions. So first of all, I have to tell you what the supercharges look like in 4 dimensions. So the 4D supercharges, I will call them Q alpha again, but now alpha is going to be a two-component left-handed Weil spinor index. So now you hopefully know precisely what this notation means, at least in 4 dimensions. And I'm going to put an additional label, little I, which is going to cycle through the different supercharges if we have more than one. And I will always take this label I to run from 1 to script n. And if there's no other convention that's consistent in supersymmetry, it's always that script n labels the number of supersymmetries in units of the fundamental spinor in whatever dimension you're in. Okay? So that part is good. The bad part is that the dimension of the fundamental spinor changes as you go between different dimensions. So the actual number of supercharges will be some multiple of script n, which depends, unfortunately, on the space-time dimension. So, for example, n equals 1 in 4 dimensions will not be the same amount of supersymmetry as n equals 1 in 3 dimensions. That's the price you have to pay for this uniform notation here. So because of this, and I will do this throughout, it's also very convenient to not only work in terms of script n, but also to introduce a second quantity, let's call it capital N sub q, which is the number of real supercharges. And by the way, I should have emphasized this, and hopefully it was already clear over here. These two-component Weil spinors in Lorentzian signature in 4 dimensions are complex. So similarly, the q's here are complex. There's no reality condition you can impose on them. I'll write down their complex conjugates in just a second. And so if we want to actually count the number of real supercharges in this 4-dimensional setting, we'll have to, of course, multiply everything by script n, and then we'll get one factor of 2 because they're 2 spinor indices, and then we'll get yet another factor of 2 because the q's are complex. So in 4 dimensions, the number of q's is 4 times script n. And supersymmetry comes in units of, number of supercharges jumps in units of 4. Question? No. Okay. So at this stage of the discussion, and for a little while, the number script n will be completely arbitrary, and everything I say will hold for general script n. But at some point, we'll see that there are actually physical principles that restrict the allowed values of script n. Probably by the end of today's lecture. Okay, so recall that Hermitian conjugation exchanges left-handed and right-handed Weil spinors in 4 dimensions. So the Hermitian conjugates of the q's, qi alpha dagger, are going to be dotted spinors. They're going to be right-handed spinors, and we're going to denote them by q bar, lower alpha dot. And I'm just going to take it as a convention for now that Hermitian conjugation also lowers the I label. At this point, this is just a useful convention. So these are the Hermitian conjugates of the q's. And I think now we have everything in place to write down the actual supersymmetry algebra. So let me do that over here. Oh, so much easier. Okay, so finally, the Susy algebra in 4D, we have three different commutators to consider. We can consider the commutators of Q's with Q's, Q daggers with Q daggers, and Q's with Q daggers. So Q's with Q's are easy. They just anti-commute. And I'll have to say a little bit about that in just a second. And if we decided that the Q's commute, then of course we can take the Hermitian conjugate of that equation and conclude that the Q bar is also anti-commute. And the really non-trivial anti-commutator will be the one between Q and Q bar. So in the conventions that I'm following, which are the conventions in the book by Wess and Bagger, the supersymmetry algebra looks like this, where this sigma matrix with one dotted and one undotted index is the same matrix that I used before to convert from vector to bispinner notation. And for most purposes, you don't need to know explicitly what these matrices are, but if you want to be explicit about it, you can pick a representation in which the 4 vector sigma mu has entries -1 in the first slot, and then the Pauli sigmas in the spatial components. Yes, please. Yes, thank you. There's also a very important delta ij. Okay. And just for future reference, let me state it now so I don't have to remember to state it later. I'm always going to use a metric convention in which is mostly plus. Okay, so let me make a couple of comments about this. The first comment, which is just terminology, is that the algebra with script n equals to 1, when we only have a single supercharge, is always referred to as minimal supersymmetry in the given space-time dimension. And the cases where, with n bigger than 1 are referred to as extended supersymmetry. A more important thing, which I wanted to remind myself with these dots, is that there can be additional operators or charges that appear on the right-hand side of this algebra, of these anti-commutators. And it turns out that those are totally anti-symmetric in the momenta. So here, both here and here, they can be extra terms on the right-hand side that are tensorial charges with vector indices, let's say little n vector indices that are totally anti-symmetric in the vector indices. So these are like n-form charges. And I have omitted them from my algebra, and I'm not going to be discussing them in detail, but I wanted to tell you about them, and because you'll see them in textbooks and papers, and also mention what they're good for. So a tensorial n-form charge is associated with what is now called an n-form global symmetry. An n-form global symmetry is a generalization of an ordinary global symmetry, where a standard internal flavor symmetry that you're probably most familiar with is called a zero form. That's when this z doesn't have any indices and it's just a scalar charge. And the objects that carry charge under such an n-form global symmetry are n-branes. So those are dynamical excitations whose world volume has dimension n+1. For example, 0 branes are particles, 1 branes are strings, and so forth. So these z's are activated by n branes, and the fact that they appear in the supersymmetry algebra is what makes it possible for these branes to be BPS, meaning that they are annihilated by some fraction of the supercharges. I'm not going to explain that in detail here. We're going to have an example of supersymmetric representation theory in a little bit, where I'll remind you what BPS means. But the fact that the supersymmetry algebra allows BPS branes, BPS particles, BPS strings, and so forth plays a tremendously important role both in Susy QFT and also in string theory.
These are somehow related to the is essentially leaving the world volume with the EVA.
Well, there's an important thing that we have to decide, which is whether these n-form symmetries are gauged or global. This situation that arises in string theory most naturally is the one where they're gauged. But that's also the situation where the supersymmetries themselves are gauged and you're really in supergravity. So then this algebra would be like the kind of asymptotic symmetry algebra of supergravity, and all of these would be gauge charges. And of course, for example, the D branes in string theory carry these higher form gauge charges. But in supersymmetric quantum field theories, which is the setting that we're discussing, there's no gravity, there's no supergravity, and all of these will be global symmetries. The Q's will be global symmetries, and also the Z's will be global symmetries. And nevertheless, there's a sensible notion of what it means for a brane to be charged under such a global symmetry. Yeah. The most familiar setting, I think, is just the ordinary central charge that can arise when there are no tensor indices whatsoever. For example, in n equals to 2 theories. Yes, please.
Where exactly the Z enters in the algebra, actually understand.
Could you please repeat?
How exactly the Z enters in the algebra, like QI, QR or repeat a computer?
Well, for example, there is another term you could write on the right-hand side here, which looks a little bit like a momentum, but is in fact a Z charge with one index. And that will be a one-form charge. And that gadget will be carried by a string. Also here, in this anti-commutator, because you have both the I indices and the alpha indices, you can choose to symmetrize the alpha indices. You can choose to write here, for example, a central charge, or a Z charge, which is symmetric, which is anti-symmetric in the I and J indices, and symmetric in the I and J indices, and symmetric in the alpha beta indices. You see, these are internal indices, these are space-time indices. The Z's have to be simultaneously symmetric under the interchanges of the pair I alpha and J beta, because this is an anti-commutator, so that's why I wrote them like this. Now, an object with two symmetric spinor indices is something we haven't discussed yet. But in fact, it turns out to be related to a two-form. If you transform back to tensor notation, this is a two-form, in fact, a self-dual two-form. So you see that just from the Lorentz structure, it's perfectly possible for these higher Z's to appear. And this two-form charge is carried, for example, by BPS domain walls.
These chapters are related to Northern Church?
Sorry, can you say that again?
These chapters are related to Northern Church?
To what? Noether charge?
Yeah.
Yeah, actually they are. They are related to the Noether charge for the higher form symmetry transformation. How exactly you write that out in detail is a little unusual, but yes, absolutely. Okay. Part of the reason I wanted to bring this up is because it appears all over the place, but the other reason is that we may or may not get an opportunity to mention these higher form symmetries in one of the later lectures. Okay. So the next thing I need to explain is the business with flavor symmetries and R symmetries. So ordinary quantum field theories, of course, can have standard internal symmetries. In the language of these higher form symmetries, these will be called zero form symmetries, but they're exactly the kind of symmetries you've always known. For example, chiral symmetry was mentioned in Balt's talk. If you take QCD with massless quarks, there's a nice chiral symmetry, which in that case would be spontaneously broken. But that's a nice internal symmetry that acts on local operators and on particle-like excitations in the theory. But in supersymmetric theories, we need to additionally make a distinction between different internal symmetries of this kind according to whether or not they commute with the supercharges. So an internal symmetry always commutes with translations and rotations. That's in some sense the definition of an internal symmetry. But if you're in a supersymmetric theory, you also need to decide whether or not it commutes with the Q's. And so this is where this distinction in supersymmetric theories between flavor and R-symmetry comes from. In ordinary quantum field theories, you would not make this distinction, and you would just call all of them flavor symmetries. So R-symmetries are just examples of flavor symmetries, but it's useful to keep this terminology separate. So this is now the Susy terminology. I'll call something a flavor symmetry. Let me schematically denote the charge by script F or something like that. If script F commutes with all the Q's. And by complex conjugation, also with the Q bars. And what that means is that if you have multiplets of supersymmetry, if you have multiplets of different states or operators related by the action of the Q's, which we'll discuss in just a little bit, all of these states in the multiplet have to transform in the same way under the flavor symmetry. So supersymmetric flavor symmetries apply to entire supermultiplets at a time. And all the states in the multiplet have the same representation. By contrast, anything that doesn't commute with supersymmetry we refer to as an R-symmetry. Any internal symmetry that doesn't commute with supersymmetry we'll refer to as an R-symmetry. So if I schematically denote the R-symmetry generators by big R, then the commutator of big R with the Qi is not 0. So what does this mean? In particular, this means that different states in the same supermultiplet do not need to carry the same R-symmetry representation. Now, if the commutator of the Q's with R is not 0, then what is it? Well, there's not that much it can be, almost by Lorentz invariance. The R's are Lorentz scalars, and the Q's are left-handed Weyl spinners, and the only left-handed Weyl spinner charges we have lying around at the moment are the Q's themselves. So the only conclusion is that the Q's actually form a representation. Let me see if I get this straight. Upper I, lower j of the R-symmetry. So the Q is just transformed some nice representation under the R-symmetry. Sometimes what we also say is that the R-symmetry acts by automorphisms on the supersymmetry algebra. What exactly that means we'll see in a couple of seconds. Yes, please.
So is there any particular reason that in quantum field theory you don't have internal symmetries that commutes, but in supersymmetry there is a possibility of having, or is it just a choice?
No, it's really a matter of terminology. You see, yes. Let me repeat the question. The question was, let me rephrase the question. The question was when this notion of an R-symmetry makes sense, with or without supersymmetry. You see, without supersymmetry, it's a moot point to discuss what the commutation relations of a flavor charge with the supersymmetry generators would be, because there are no supersymmetry generators. So in that case, you would refer to either one of those as a flavor symmetry. In supersymmetric theories, you do have the Q's, and so you have to decide whether you're in the case on the left or the case on the right. So it's a matter of convention to refer to internal symmetries that commute with Q as flavor symmetries, and to refer to symmetries that do not commute with the Q's as R-symmetries. But from the point of view of a non-supersymmetric field theorist, they're completely indistinguishable.
Yeah, but it's conceivable that you have certain generators in quantum field theory that does not commute with all the Lorentz generators, right? I mean, you possibly could have that in a quantum field theory.
You could also have space-time symmetries that are not of the usual type, but that's not a situation we're discussing right now. I'm considering just internal symmetries, things like, chiral symmetry and so forth. Things whose charges are Lorentz scalars. Yeah. Okay, so if the R-symmetry if the Q's are in a representation of the R-symmetry, all this means is that under the action of R, the Q's map with some matrix Uij, like so. So here I've roughly speaking written the infinitesimal action of the R symmetry. Here I'm really considering the sort of finite exponentiated action. So U is just some matrix of complex numbers. And if we decided that the Q's transform in this way under the R symmetry, we must then check that this action of the R symmetry is compatible with the structure of the supersymmetry algebra. Okay? So we must make sure that the form of U is such that it preserves the anti-commutation relations that we wrote down over here. So the QQ and Q bar Q bar ones are completely fine because they're just homogeneous and 0 maps to 0. But making sure that this one remains invariant is a little bit non-trivial. It's just a few lines of calculations, so I encourage you to check this for yourself. But if you plug in the transformation rule for Q here, and also the corresponding transformation rule for Q bar, which is just obtained by complex conjugation, so I can write it as, if you wish, U upper I lower j star times Q bar alpha dot j, or by interchanging the indices, U dagger upper j lower I Q bar alpha dot j, and then it's more natural to think of the U dagger as acting on the right. So then if you plug into these commutation relations and you demand that they remain invariant, what you'll find is that the necessary and sufficient condition for this to happen is that this important delta ij symbol that we had over here is actually invariant under this transformation by U and U dagger. So in other words, we have to demand that U I prime, U j j prime, delta I prime j prime is delta ij. So U acts on the indices of the delta symbol, if you wish, and the condition for the algebra to be invariant is that algebraically delta ij is an invariant symbol of the this transformation rule. Okay? This point of view will be useful when we discuss all the other cases in different dimensions. And by definition, a complex matrix that satisfies this is necessarily a unitary matrix, because this is nothing but U dagger ij, and the right hand side is the identity matrix. So we learned that, in fact, the R symmetry transformation on the supercharges must be a unitary matrix, and so this object Uij over here is an element of the unitary group U script n. Right? I and j run from 1 to script n, so U is an n by n matrix. Okay. Let me make one more comment about the R symmetry before we move on and discuss what this story looks like in other spacetime dimensions. So what we have assumed here is that the R symmetry is, roughly speaking, as large as it possibly can be. So we've derived the most general transformation rule for these R symmetries that don't commute with Q. But nowhere was it said that a given quantum field theory that you want to study actually possesses such an R symmetry. There's nothing that we have said so far that forces it to exist. And the reason for that is that, as I've said before, the R symmetries themselves do not actually appear in the supersymmetry algebra. Right? If you look at the QQ commutation relations, R never appears on the right-hand side. Instead, all we said was that R acts on the Q's to give you a representation that's consistent with the supersymmetry algebra. That's what it means for the R symmetry to be an outer automorphism. But whether a given theory actually has some amount of R symmetry, anywhere between the maximal amount that we derived and nothing, depends on the theory in question. This will change dramatically once we start discussing superconformal algebras, which are the fusion of the supersymmetry algebras here with the conformal algebras that you already heard about in Balt's lecture. Okay, but before we get there, let me quickly sketch how this story goes in dimensions other than 4. So I promised you I'd give you some quick tour of 3, 4, 5, and 6 space-time dimensions. So we're just going to repeat this logic in those other dimensions, but we'll be fairly quick about it. Any questions about this before I move on? All right, let's discuss 3D. In 3D, the Lorentz group is SO31, and the double cover spin group is SL2R. So now it's SL2R rather than SL2C, which it was in 4 dimensions, which means the structure is fairly similar. We still have, as a basic spinor representation, the 2-component representation, except there are a few differences. First of all, there's no chirality in 3 dimensions, so we don't refer to this as a Weil spinor. It's a Dirac spinor, if you wish. It has 2 components, which is the number of components that a Dirac spinor has in 3 dimensions. But because SL2R is real, it's actually consistent to impose a reality condition on psi. So the minimal spinor in 3 dimensions is a real 2-component spinor, and we conventionally refer to this as a Majorana spinor. Majorana fermion. So the minimal spinor in 3 dimensions, as promised, only has half of the number of the components that a minimal spinor has in 4 dimensions. The supercharges, just like in 4 dimensions, are going to be minimal spinors, Q alpha, and the number of minimal spinors is indexed by the index I, which, as I said before, always runs from 1 to script n. But now the Q's obey the same reality condition as I wrote for the size over there. And because the number of components of the minimal spinor is 2 real components, the relationship between script n and the total number of supercharges is now 2 times script n rather than 4 times script n, which it was in 4 dimensions. Okay. So with this in mind, we can write down what the supersymmetry algebra is in 3 dimensions. The supersymmetry algebra is simply Q alpha I, Q beta j. Because the Q's are real, there are no Q bars, so this is it. And now in the conventions that I'm going to use, I'm going to write a delta ij with upper indices, and then there's going to be a gamma mu p mu. It's going to look structurally very similar to 4 dimensions, except now my gammas are really genuine 3-dimensional gamma matrices. And the index structure is as follows. There's a lower alpha index and a lower beta index. But it turns out that the gamma matrices in 3 dimensions are always such that when you write them with lower indices like that, they are symmetric. And that's good because this gamma symbol is supposed to translate the 3 momentum, which has 3 components, into some equivalent bispinor expression. So we also want that to have 3 components. And this has 3 times 4 divided by 2. Let's see. What did I say here? What is happening? I was going to make a great point, and I'm getting confused about it. Right, so it's true that this has 3 components. And it's also true that the gammas are symmetric. Sorry? Gamma are the real, these are the real gamma matrices, yeah. They're real because SL2R is real, so I can always choose my gamma matrices to be real. Okay. Thank you. That's the answer. Alpha runs from 1 to 2. So 2 times 3 divided by 2 is the number of components of a bispinner. Symmetric bispinner is 3. See, Balt is way more awake than I am. Thank you. Good. So again, just like in 4 dimensions, we have a one-to-one map from a bispinner to the momentum vector. Except that in 4 dimensions, this thing had one dotted and one undotted index, which didn't have anything to do with each other. Here, they're indices of the same type, but they're symmetrized. And that's important because, you see, because of the structure of the anti-commutator on the left, the whole thing has to be symmetric under the simultaneous exchange of alpha I with beta j. Right? If you simultaneously exchange these indices, then you're just swapping the q's in the anti-commutator, and that doesn't change anything. And because the gammas are themselves symmetric, it means that the object, the matrix with I and j indices that sits on the right-hand side here, also has to be symmetric. And what that means is that you can actually choose a basis in which it's just delta ij. Won't have time to go through that. If you want to go through it in sort of complete generality, starting from essentially no assumptions, that's the point of view that you can read about, for example, in Weinberg's book. But once you arrive at that point, life is pretty simple. Once you decide that the invariant object that appears here is a delta ij symbol. Because now we can repeat the logic about how the R symmetry works from 4 dimensions. Remember, the logic was as follows. The R symmetry just maps the q's to themselves multiplied by some matrix uij. But now the q's are real, and that also means that the uij's have to be real. These are real n by n matrices. And now the only thing we have to demand is that they leave this algebra invariant. And just like in 4 dimensions, that boils down to the requirement that delta ij is an invariant symbol of this transformation. So if you have a real n by n matrix that also leaves delta ij invariant, that is the very definition of the special orthogonal group. So in fact, the u's are not just real n by n matrices, they are matrices in SO script n. So this is a rather quick route to seeing that the allowed R symmetry in 3 dimensions for n extended supersymmetry is necessarily a subgroup of SON. As we said, in 4 dimensions, it's not obvious that the entire SON is actually present or realized, but that's the maximal group it can be. Very good. So that's all I wanted to say about 3 dimensions. Any questions? At least for now. Sorry?
Why do we need the superscript?
Which superscript?
It's SON to the...
That's not a superscript, that's an unerased. That's an unerased thing from a previous generation. Sorry.
Is the SO2 combinable?
Yes. Thank you.
Obviously, there is a special group between one or is just other one?
Well, I guess I should have said, I'm here discussing the R symmetry that's connected to the identity. Yeah. You're right. We could discuss global flips as well. Okay. Just 2 more to go. I think we'll manage today to do that. So let's go to 5 dimensions. So in 5 dimensions, we're going to use the fact that the Lorentz group is SO 4, 1, which up to a Wick rotation is the same as SO 5 if you insert some i's. And there's an interesting exceptional automorphism that relates Lie algebras of low rank. And one of the examples of this exceptional automorphism is the fact that the SO5 Lie algebra is the same as the SP4 Lie algebra. And I'm using here a convention in which, by the way, well, in particular SP4 is SO5, and that also means that SP2 is the same as SU2. And in general, the rank n symplectic Lie algebra is SP2n. Some people don't put the 2 here, and that sometimes leads to confusion. So that's why I wanted to mention it. Very good. And the important thing is that a spinor of SO5 maps under this equivalence to the fundamental representation box of SP4. Right? SP4 is the 4-dimensional symplectic group, so its fundamental representation is 4-dimensional. And that's the same dimension as the basic Dirac spinor of SO5. So that's very convenient because now we can just use fundamental SP4 indices instead of worrying about gamma matrices and spinors of SO5. So that's going to lead to a notation that's fairly similar to the one we used in lower dimension. So the basic spinor psi lower alpha now has 4 components. And this is, if you wish, a complex Dirac spinor. Now, it turns out to be impossible to impose any reality conditions on Dirac spinors in 5 dimensions. So this is really a complex 4-component object, which means it has 8 real components. And there's no real way to make this number any smaller than 8. But there is an interesting way of repackaging the information in psi alpha, which will be particularly useful when we write the supersymmetry algebra. And the way you do that is you introduce an object known as a symplectic Majorana spinor. So what do those words mean? Well, Majorana usually means that there's a reality condition involved, but I just told you that there isn't a reality condition we can impose on the psi alphas themselves. Instead, what is possible is to introduce an object that has both an alpha index running from 1 to 4 and an I index running from 1 to 2, which is just an internal label at this point. Has no group theoretic meaning just yet. And it turns out that you can repackage the components of psi into this 2-label object. Now, superficially, this object has twice as many components as psi alpha does, but in fact it turns out to be possible to impose a reality condition on this gadget to cut it back down to 8. So the symplectic Majorana condition is the condition that the complex conjugate, or the Hermitian conjugate of psi alpha I, is proportional to what I'll sometimes write as psi lower I upper alpha, which is the same as the original spinor. But if you want to lower the I index, you use the 2-dimensional epsilon symbol to do that. And if you want to raise the alpha index, you use the SP4 symplectic invariant tensor omega alpha beta. If you haven't seen these before, let me just remind you. I mean, this one is obvious. Epsilon is the Levi-Civitas tensor on 2 indices, so it's just proportional to 0, minus 1, 1, 0. And omega alpha beta is a 4x4 matrix that is invariant under the action of SP4. It's a 4x4 symplectic matrix. So again, you can take it to be proportional if you wish to 2 blocks of this form. There are many other convenient representations as well. And this is a gadget that you can use to raise and lower symplectic alpha beta indices. So this, it turns out, is an acceptable reality condition. And it cuts the number of components of this psi alpha I down from 8 complex to 8 real, which is the same number we had here. But this way of writing it will turn out to be much more convenient because it'll make the R symmetry properties of the theory more manifest. So the basic spinner and the basic supercharge in 5 dimensions will be a symplectic Majorana spinner. Okay, so now we can repeat the same game we've been playing. The supercharges Q alpha will be symplectic Majorana spinners. A basic symplectic Majorana spinner runs from 1 to n. If you want, sorry, from 1 to, I runs from 1 to 2. If you want n of them, then I runs from 1 to 2n. So always over an even number of I indices. And again, n is the number of minimum symplectic Majorana spinners. And all of them satisfy this type of reality condition. The only difference is that because now the number of I indices is 2n rather than just 2, I need to replace the epsilon symbol, which you can think of as the invariant symbol for both SU2 and SP2. I need to replace that by the invariant symbol of SP2n. So the general symplectic Majorana condition is that Q alpha I dagger is proportional to omega ij, omega alpha beta, Q beta j. So this is the SP4 invariant symbol associated with spinner indices, and this is the SP2n invariant symbol associated with the I indices. Very good. And with this in mind, the number of supercharges we have here, NQ, is 8 times script n. Right? Now the basic symplectic Majorana spinner has 8 components, and script n counts their number. So now we can write the supersymmetry algebra as follows: Q alpha I, Q beta j. Well, what can go on the right-hand side? Again, there's some 2. The first thing that has to go on the right-hand side is always the momentum. And then you need to contract with the gamma matrix to give it the right bispinner index structure. So let me just write that again as gamma mu. But it turns out that in 5 dimensions, unlike in 3 dimensions, where gamma was symmetric, in 5 dimensions it's anti-symmetric. But that's not quite enough, because you see P mu in 5 dimensions has 5 components. But alpha and beta run from 1 to 4, and an anti-symmetric matrix with 4, a 4 by 4 anti-symmetric matrix has 4 times 3 divided by 2, which is 6 entries. So that means that this gamma matrix has to satisfy some additional constraint, and indeed it does. You see that the omega alpha beta matrix, which is an invariant matrix of the spin group, is also anti-symmetric. So you can take the omega trace of gamma alpha beta, and that turns out to be 0. So that's how the bispinner version of this momentum operator has the same 5 components as the vector version does. That's not going to be super important in what we do, but it's the same counting trick we've been using so far. Now, since we know that gamma is anti-symmetric, and we also know that the left-hand side has to be symmetric under the simultaneous exchange of the alpha I and beta j indices, means that we necessarily have to put some anti-symmetric matrix in I and j indices here. And just as before, I can essentially do a change of basis to guarantee that this anti-symmetric matrix is itself the omega ij matrix that already appeared in the symplectic Majorana condition. Just as in 3 dimensions, if you wish, you can put a general anti-symmetric matrix here and convince yourself later that there's a change of basis that allows you to put it in this form. This is just some game about canonical forms for different kinds of matrices. Okay, very good. So once you're at this point, life is again easy. Now you can almost do it in your sleep. If you want to know what the maximal possible R symmetry is, you say, okay, the Q's transform under some R symmetry with some matrix U, and the U matrix acts on the I indices. And the only thing I need to check is that the reality condition is preserved, and that this omega ij matrix is an invariant symbol of the transformation. But a real matrix that leaves the omega ij symbol invariant is by definition a symplectic matrix. And what that means is that the maximum possible R symmetry in 5 dimensions is SP 2 script n. Okay? So you see that there's some sort of kind of conjugacy going on between the space-time spinor indices and the R symmetry indices. All right. Let's see, how much more time do I have? 5 minutes. Oh, that's great. And then we can do 6 dimensions, and then we can call it a day. So 6 dimensions is very similar to 5. There's just one additional caveat, which is that in 6 dimensions there is a notion of chirality, which we'll have to deal with. Okay, so in 6 dimensions, the Lorentz group is SO51, and the Euclidean form is SO6. And there's again a nice exceptional automorphism between SO6 and SU4, such that the spinor of SO6 is identified with the fundamental of SU4. And in fact, the more precise way to say it, which is the way I wanted to say it, is that the chiral or left-handed spinor of SO6 is associated with the fundamental of SU4, and the right-handed spinor is associated with the anti-fundamental of SU4. So now we genuinely have to distinguish between left-handed and right-handed spinors. The left-handed spinors I'll denote by psi with lower alpha indices, just like in 5 dimensions, alpha runs from 1 to 4. And the right-handed spinors I'll denote with upper indices. And these really transform differently now in the fundamental and anti-fundamental of SU4. Or if you're in Lorentzian signature, the appropriately Wick-rotated version of SU4, which has some non-standard reality properties from the point of view of SU4. Yes, please.
I have one stupid question, because you talked about SO14.
So what?
SO14, 5 dimensions.
Yeah.
And so here you talked about reality conditions, right?
Yeah.
So you derived it from SP4.
Yes, in 5 dimensions.
So my question is, all the reality properties you mentioned, is it property of SO5 or SO14?
Well, the reality conditions I mentioned are properties of SO14 with the standard reality, or SP4 with a non-standard reality. So it's not the compact form of SP4. Similarly, the SO51 here does not give you the standard compact form of SU4. It gives you SU4 with some funny eyes and some, right? The thing that's literally the same compact real form as SU4 is SO6. So the same eyes you put in place to go from SO6 to SO51, you can put in SU4 to give you the Lorentzian version of SU4, if you wish. I don't know if SU4 with that kind of reality conditions has a good name. Some people call it SU4 star, I think. Okay. So now we have left-handed and right-handed spinors, and in general they are again complex. And it turns out that just like in 5 dimensions, there is a way of trading these complex spinors for some version of a symplectic Majorana-Weil spinor. So you can trade psi alpha and chi alpha, which are complex 4-component spinors for objects psi I alpha and chi alpha I, which satisfy reality conditions. So these are sometimes called symplectic Majorana-Weil spinners. I'm not going to spell out in too much detail what the reality condition looks like, but roughly speaking, psi I alpha dagger is again proportional to psi alpha I with some suitable matrices in front. So Hermitian conjugation really maps left-handed spinners to left-handed spinners, and similarly right-handed spinners to right-handed spinners. Very good. So with this in mind, we can now write down what the supersymmetry algebra is. But because we have chiral supercharges, left-handed and right-handed spinners, we need to now keep track of both of them. So in principle, we could have supercharges that are left-handed spinners and supercharges that are right-handed spinners. So we'll call the left-handed ones Q alpha I, and the right-handed ones Q tilde upper alpha lower I, maybe lower j. And in principle, I could have different numbers of left-handed and right-handed supercharges. So I'm going to let I go from 1 to 2n, and I'm going to let j run, 2n left, and j runs from 1 to 2n right. The reason that the number of I and j indices is even is the same as in 5 dimensions, because I traded a complex 4-component spinner for this type of symplectic Majorana-Weil gadget, which doubles the number of I indices. Okay? So now we can write down what the supersymmetry algebra is, and that will be a nice endpoint for the discussion today. The left-handed Qs, it turns out, completely anti-commute with the right-handed Qs. And amongst themselves, they do something which looks awfully similar to what we had in 5 dimensions. We have a symplectic matrix Ij, and then we have a gamma matrix contracted with a momentum. And just like in 5 dimensions, the gamma matrix is anti-symmetric in the spinor indices, alpha and beta, and that's why the Ij matrix that sits in front is again also anti-symmetric. The number of components also works out here, because remember that in 5 dimensions, alpha beta anti-symmetrized had 5 components, but it also satisfied a tracelessness condition. In 6 dimensions, you just drop the tracelessness condition, and you get the 6 components of P back. So this is the commutation relation of the left-handed Qs, and there's a completely analogous one for the right-handed Qs. So at this level, these commutation relations are structurally indistinguishable from what we had in 5 dimensions. And that means in particular that the argument we gave there for what the R symmetry was is exactly the same. The only difference is that we now have Qs and Q tildes. So the argument we gave there showed that the Qs transform under an SP 2n left R symmetry. So there's an SP 2n left acting on the Qs. And exactly the same argument shows that the Q tildes can at most transform under an SP2 and right R symmetry. So the maximal R symmetry compatible with the 6-dimensional supersymmetry algebra is SP2n left times SP2n right. And that's all for today.